Hello, this is Team CD13 and we are presenting our iMaking Challenge project.
For week 2, for the CAD model, we decided to start from scratch and create a new file. In this CAD file, we started with the moving parts, aka the gears, wheels, and the nut on the threaded rod. Once we were satisfied with the way they interacted with each other, we built the rest of the vehicle around them. We also made a few changes, such as taking off the mud guard as they were purely aesthetic, and putting the spring in the middle of the vehicle to keep it straight even after the impact with the wall.
After scenario 1, we decided to stick with the same motor, which has a no-load speed of 8,478 RPM, powered by the batch of 6-volt batteries. Our reverse mechanism consists of having a spring attached to the front of our car. The spring will be attached to a reverse DP/DT switch. Once the spring reaches the wall, it will start to compress against it, then activate the reverse switch and make the car go back.
We chose to make a set of compound spur gears that were commercially available, ranging from 7 to 40 teeth with a module of 0.5. As the aim is now for our vehicle to be the fastest, we decided to decrease the ratio to 87:1, which will be explained later on. Moreover, we increased the diameter of the supporting axles to ensure better stability and less losses.
In order to make our vehicle come to a stop, we have chosen to create a thread on half of the back wheel's axle. By restricting the motion of the combined nut and bolt to a single direction thanks to the hole in the body, we have ensured that once the vehicle has traveled the desired distance, the wheels will no longer be able to turn, thus causing the vehicle to come to a full stop.
For this project, we had to respect a few regulations, starting with the budget limit. We have submitted a more detailed bill of material, but here we can get a general idea of what the £30 budget was spent on. And we can see a few of the logos of the website used to find the needed materials. We also respected the constraints given to us for the materials to use, as you can see here, for example, with the battery.
In terms of size, our vehicle fits well within the restrictions, as you can see on the screen. In terms of reducing slippage, as the aim was for our vehicle to be light, we chose a motor with a relatively low stall torque, allowing us to overcome the slippage in less than 0.02 seconds, significantly below the 10-second boundary imposed.
We then analyzed the forces acting on the body to estimate the vehicle's energy usage. By adding the drag force and the rolling resistance to the net force, we can obtain a value for the driving force R. This value is then multiplied by the distance traveled to find the time rate of change of energy usage. Finally, by summating all the delta E's, we obtained a final energy usage of 1.05 joules.
We decided to analyze different gear ratios with regards to their energy usage and max velocity. As you can see, a lower gear ratio means a higher max velocity but consumes more energy. We use these graphs to find the best compromise between energy used and max velocity. In the end, we chose a gear ratio of 87:1 because it used the amount of energy we were aiming for, and the gears were more commercially available.
Our vehicle initially weighed 0.7 kilograms. Even though we were satisfied with a maximum velocity of 0.37 meters per second, the energy consumption was not optimal. We changed the material of the body to birch wood and cut off the excess material from our initial design and reached a final weight of 360 grams. Our maximum velocity was comparable. However, we obtained an energy consumption of 225 watts instead of 370, which is an impressive improvement.
In order to choose our spring, we decided to compare the energy used when using different spring constants and lengths. We came to the conclusion that this parameter did not affect the energy usage significantly. We therefore chose to use a spring enabling a suitable deceleration to activate the reverse switch, and that was commercially available for our dimensions. A 36 millimeters long spring with a constant of 220 newtons per meter.
Thank you for watching.